Let's take a look at the second lecture series on the part 2 for Intro to Hydronics. So we're going to, all right, so we're going to take a look at, start out with the objectives in this one. So primary types of hot water system, we're going to take a look at those and their components. We'll look at a basic gravity system and a force system, and just kind of the difference between the two. We'll look at the different types of boilers used, primary boiler components, and then we'll look at some other things related to air and water control on this system. So let's start out with the gravity system to identify specifically what's going on in here. So on the gravity system, we've got a system where we start out with my boiler and we progress through the supply system, and we've got this system right up here, and as you can see, what we're doing is we are progressing and we're sloped upward. We're relying on completely on buoyancy. So all of my terminal units are going to be above the mains as they progress. And so you've got a supply that runs up into this particular unit, and then we have a return that as that water cools, it is more dense and it will tend to flow into the main of that system. So that would be one of the ways that that first terminal unit is going to gain. Now, there's some other things that are going on in here. On this system here, we're also relying on what we're going to call kind of an open expansion tank to some extent in here. That is going to allow us, and this is in the top part of the system. So what that's going to allow us to do is allow for the safe expansion of the fluid or the water in my system. So as that water expands, we're going to see the water level kind of get a little, go a little bit more and a little bit more. And as it expands and as the water cools down, then it'll obviously decrease the amount of water that's in that. So these are generally going to be systems that are certainly less, certainly a less efficient type of a system. Generally, most systems are not going to function in a manner like this. However, I think we need to be aware of the fact that understanding the concepts of how does gravity move through a system? How does the water how does it circulate in the system? And I think the point to make in there is that my warmest water is always going to want to flow to the highest part of my system, and the cooler water is always going to want to flow to the bottom on there. So you still have to have some safeties and things like that on this system, but that is one of those that is definitely a part of this process. All right, so obviously most of the get what we would probably see as normal would without a doubt be that we can heat water up, get it up to its operating temperature in a forced system, whether it's using gas or oil or any other type of system. That would be logical to see. So whether electric, gas, oil, we can heat up that fluid or the water in the system. So generally, what we're going to have to try to do is in this boiler system, we've got to control its temperature, whether it's with some sort of a sensing device, whether it's an Aquastat, something like that, and we'll look more at that. We'll use either one or multiple pumps that are going to be used to push that water through the system or circulate the water through the system is normally what happens. Now, in the first series, we talked about how if we knew the BTUs load of a structure on an hourly basis, we can very easily figure out what the flow rate is. So that would be, and basically the flow rate helps us determine how big of a pump that we need. So between the resistance of the piping system and the flow rates for the system, that's going to help us pick that pump. And that's what they mean by, in this one here, the pumps are, would be sized to satisfy the flow requirements for that system. All right. Forced water systems are also used to in the building you would typically see multiple zones. We're not going to see just one zone in most cases. Usually you'll see more than one zone. So when that happens to be either A, I'm going to open up some specific zone control valves, or I'm going to and then start a pump or multiple pumps, or I might have multiple pumps and not use zone valves. Typically that's kind of the way that would be going. And then our circulating pumps will obviously move the fluid. Once those devices either are energized or open, they will then move that fluid directly through the piping system, through the boilers, through the terminals, things like that. So that's kind of generally how that will end up working. Our terminal devices would be like our heat emitters, and that's essentially what would allow us to move that energy to the cooler surrounding air around those devices. And those devices could be fan cooled, or they could have air that they're moving through those as far as over those heat exchangers to extract that heat, but they don't have to. They could just be natural convection air currents like a typical residential baseboard might deal it. Their turn lines obviously have to move that water that leaves those terminal units back into the boiler, and there's multiple ways we can look at that. And then obviously once that cold air comes in, if there's still a heat demand, or that cold water comes in, then we need to reheat that water. So in this particular image, what we're looking at here is a system where we're going to take, let's go ahead and change the color of that one here. And I'll make that one there. Okay, all right. Yep, that'll work. So there we go. All right, so what happens here is on this system here, this one is showing a boiler supply system coming out of here. They're showing a circulating pump. This is just mainly just to identify essentially elements of a four-star system. And so they have a circulating pump. The job of the circulating pump is let's get the fluid moving. So in this system, because we have multiple zone valves with a single pump, we have to open up either one or both of these two zone valves before we can circulate any fluid. So in this first one, if that one is open, that's going to move the fluid through the system if you follow the arrows, and it's going to move that into the first baseboard or first terminal unit and then go right back and start the return. Now this is actually piped very similar to a commercial application that would be considered as a reverse return. We'll look at those more later. As you progress through the next unit, we go through the terminal unit and you jump right back into the return and you make its way. And the third one would be the same way. You make its way back into here. And as we obviously, after you go through the heat emitters, you'd expect that water to be cooler. Typically it might be cooler by 20 degrees or so. And then all of your additional returns are going to come back into here. There will likely be a balancing valve of some sort. There may be a check valve. The check valve would, in this application here, would primarily be used to avoid or minimize the amount of gravity circulation that, so that when during the off cycle, we don't have a problem where we get water migrating backwards up through the return if it's warmer than the water that's within this circuit. So the check valve is primarily used there. And of course, there's other things that have to go into the system as well. So let's take a look at some of the other devices that are important. So in my makeup water line, where my fresh water comes from the well or the city, the municipal supply, whatever that might be, we will typically have to have some sort of a backflow preventer on that system. And that backflow preventer, you could almost think of that as like a check valve. So it will not let the water flow backwards this way towards the city. It will only allow it to go in this manner. So that's a one-way check valve. And that's designed so that in the event that you had contaminated water in your piping system, which would be typical, it would be, you don't want that going into your drinking water. And that's the purpose of the backflow. There is such a thing also as a pressure reducing valve. And on the pressure reducing valve, The pressure reducing valve is designed to take that high pressure water from the well or the city municipal supply and reduce it to a more usable pressure. Typically, that usable pressure ends up being approximately about 12 psi in that area, which is fairly typical. They also have a safety relief valve on most of these systems. That safety relief valve typically relieves it at normally around 30 psi for most low pressure residential boiler systems. Of course, there's also a temperature pressure gauge, and it will do just that. It typically reads some temperature of the boiler water, and it also will give you an indication of what the pressure in that boiler system is. And the last of the devices that we'll take a look at is the expansion tank. And the expansion tank in this application is intended to allow for the safe expansion of the water as the boiler system is warming up, as the boiler is adding heat to this. We need to allow for that expansion. So a lot of the current tanks, what they actually do is they will have a bladder in this system that as it heats up, it'll as that water expands, it takes an air cushion on this side and it actually pushes that diaphragm directly towards that air and it compresses it. And that's typical of anything that we would put in current today. So let's talk a little bit about some of the boilers and see exactly how we do this. So this first boiler system that we're going to look at here is either you could deal with either cast iron or copper fin type boilers, whatever it might be. But let's take a look at the two basic boiler systems. So on this first system that we're looking at here, we've got let's call it a copper fin tube type boiler. Now, a couple of things that I want to point out on this copper fin tube boiler is they are very, very low in mass. They do a pretty good job of minimizing the amount of heat that's just sitting in the boiler due to the high mass of the boiler, and they generally have quite a bit less water inside the boiler. So it's generally designed, we consider those as more of a low mass type of a boiler. And I'm going to go ahead and change my marker a little bit here. So copper fin boilers, one of the things that's pretty nice about it is as I fire this boiler up, the recovery and the speed of the recovery that what it takes to warm up those copper tubes, these fin tubes that we're showing right here, those are all copper tubes. So the fluid or the water has to flow through those tubes, and the flame generally goes around the outside of those things. So it has a very, what I would say is the volume of water is fairly low, and it really, it can heat up the water very, very fast. So you don't have a lot of standby losses. But there is something that you do need to definitely be cognizant of is you absolutely must, on any of these low mass boilers, water flow rate. If it's a copper fin boiler, water flow rate is very, very critical. You have to make sure you have water flow through the boiler, and preferably even having the ability to have some sort of a boiler post-purge type application would be very, very good. This boiler system that we're looking at here also is showing us that they might have some headers where the water comes in and out on some cast iron headers potentially, so on the side of that. But otherwise, it's a very nice low mass type boiler, pretty good, and it's a very popular type of a system. Not so much that it's copper fin, but in the commercial side, they're definitely that's definitely a positive one. A lot of the low mass boilers, many of them are going to be stainless steel or something other than copper. The only downside of the copper fin boilers that I would have to say is that they can have a problem where they become more susceptible to corrosion simply because of the copper fin boiler. If you run into an excessive amount of condensation, those copper fin heat exchangers on those boilers will not last very long. So that is one thing that you have to be a little bit careful of with those. People love them, the fact that they're super lightweight. And you might have an application where they might even put 2 or more or 3 of them on a job to maybe have some redundancy. So we can talk more about that later. So one of the advantages of a lot of these real lightweight boilers to some extent would be the fact that a lot of these boilers, they become wall hung boilers. They're you can have one person that carries a boiler, and if it's on a big cast iron boiler, there's no way you're going to do that. So it's really, really nice that they've reduced the mass of the boilers. They've made them more efficient to reduce the standby and the off-cycle losses, so they do a really good job on that. So that's an example of one of those. Here's another wall-mounted condensing boiler application, one that we're looking at here. And on this one here, you'll see they're showing a low mass type of a heat exchanger here, and you'll have a burner that protrudes down into a chamber that's going to be our combustion chamber, and the heat from those flames is just going to go directly to those low mass heat exchangers. And it's a great little system that they have. They're very fast in the recovery. You don't have a lot of wasted off-cycle losses. A lot of those are really very, very efficient. So it's made for very good use of energy in a lot of these applications on there. So the downside of these is they tend to become a little bit more complex. Your control systems aren't quite as simple anymore in some of these cases, and they also are, they require to have some, let's call it a little bit more of a combustion test and setup on these, more so than the other ones needed in the past. So here's another example of an install of a probably a Lochinvar system, very nice looking system. You'll notice that they're zoning it by pumps. So they have pump 1, 2, 3, 4, 5, 6 pumps on this application just for that zone. Now, one thing I do want to point out to you, you'll notice that they have a very large common header that's shown in here, and also you'll notice that there's another header down here. But the point I want to make on here is because all these pumps are pulling from this header that's right here, every single one of those circulating pumps has got to have some sort of a check valve, is the way that they have to have. So the check valve that you have to have, so in other words, on the discharge of this pump, we probably have some sort of a check valve here, 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 and so on and so forth, all the way down. Every one of those things has to have a check valve, otherwise you end up getting a circuit that potentially would pull water flow from a circuit that it does not want to have water pulled from. You want to have those pumps set up that way. Now, the beauty of this is almost all of our new pumps have an integral check valve built directly into the circulating pumps that makes it very simple and very, very easy to apply. The other thing that's really nice to see on these applications is we can also set up situations where you might have priority. So we could say, you know what, we could set up our control system such that when the thermostats call for each of these zones, they'll tell the pumps that, hey, by the way, I have a heating demand, and then in turn, your zoning panel will then tell the boiler that, hey, by the way, we have a demand. Well, what we can do is we can actually set it up where if this domestic water tank has a demand, this one will take priority, and we'll say, you know what, we're going to give you the chance to satisfy your heating requirement for this customer, and we're going to make all of you guys wait. And this controller that's shown right here, that is actually a controller that allows me to very, very simply determine using what they call a zoning controller. That system or that controller will allow me to control very, very efficiently, and just with a flip of a switch I can either give it priority or I can take priority away. So that's really very, very nice. You'll also notice on this bottom one that's shown here, they also have some PEX tubing that's probably for some sort of panel system or in-floor heating system that they would be using on there. But again, very, very nice little system. So here's another beauty that that also goes on in these systems. So one of the things that's really, really nice on a lot of these boilers is, you know, any of these wall hung boilers that are very efficient, you're either going to vent them with polypropylene, which is a higher temp PVC pipe, or higher temp plastic pipe, or you would be using PVC or potentially even CPVC. You have to watch a little bit of the temperatures that you would potentially running in those. If you're in excess of 140 degrees, which is generally the maximum for PVC, otherwise the PVC tends to create problems for you in how you know, with chemicals leaching out of the PVC. You got to be a little bit careful on that. So generally, the higher temp polypropylene is the way to go on any type of a condensing type of a boiler, unless you have the ability to manage the temperature and minimize the potential of it actually getting into a let's call it a non-condensing range in excess of 140 degrees. So that would put you at water temps that would be like 140 to 145 or higher, which would be potentially that way. The other thing that I want to point out is, you notice how you have boiler number 1 and boiler number 2. We now have built-in redundancy. So the beauty of this is, if, you know, let's say I don't want this boiler running, this one can kick on and provide us some heat, or we can use them both on here. So a lot of advantages on there. We can stage it, we can control it that way. It works really, really well on there. So one of the beauties of a lot of these condensing type boilers, or these type of systems, even like this one here, is I have the ability to achieve, you know, 95% efficient in many of these applications that are out there. So, and expanding a little bit more on here, you know, when we're talking about, typically we can vent these with Schedule 40 PVC pipe, and that's very true, but the assumption there is that your flue temps are going to be very low. And if you're starting to run inlet temperatures, you know, the thing you got to be super careful with is, and I'm going to go back to this picture. So this would most likely be my temperature, or the inlet temperature. So I'm just going to identify this one here as that. If I have a return temperature going into, if I happen to have a return temperature, and I'll use this one as the one, if I happen to have a return temperature that's going back into this boiler, and I want to keep that, what I'm going to say is a maximum of approximately 140 degrees Fahrenheit. Now the reason for that is that if I have that going in any higher than really in the 135 and 140 range, I'm going to run into a problem where the PVC pipes that are exiting your job here, that PVC pipe on the discharge pipe is going to be warmer than that temp. So that's why we want to be a little bit careful on that inlet water temp that's in there. So be very careful of that. You can lead to some heat exchanger problems with depending on the boiler. Now, in the situations where we'll run into a condensing situation, a condensing environment, you got to be, you know, we have to be aware that in some applications you may have to concern yourself with the acidic nature of the condensate and where that's going to go. So you have to make sure you're with the low pH, it's generally more acidic. The low pH would correlate to an acidic nature. We have to watch, you know, if a person had cast iron drainage systems or copper drainage systems, those systems would be eaten away. PVC would be fine, plastic piping would be fine, but any of the metals would be deteriorated. So in some cases, they will require you to have some sort of a neutralizer. So this one's showing you an inline neutralizer cartridge that would really take an acidic fluid and cause that. And we're talking about the condensate now that would come out of there, and then it would allow you to kind of make it more neutral, more like regular water. in that case. So there's a couple ways that they'll do that. All right, so let's take a look at some of our cast iron boilers that would be going on in here. So in a lot of the cast iron boilers that are in here, they do have pretty good heat transfer characteristic, but one of the problems you run into is you have to be a little bit concerned about running them for an extended period of time with too cool of a return water, where you would have excessive amounts of rusting that goes on in these cast iron sections. So you'll notice on this sectional boiler, if you need more boiler, you just pack on more sections. And these are on some of these applications, they'll even get it on a very large job. They will actually build them on site, so they can and you can have them either in vertical, you can have them in horizontal. There's a number of different ways that they'll do this, and you just have to figure out what that is. So as they talk about in here, the number of sections will vary with the capacity of the boiler. So the bigger the boiler, the more sections you have. And if it's a large enough boiler, they're going to have to build it on site, or you may not get it in the mechanical room. All right, so let's take a look at some of the devices on this boiler. So first one I'm going to deal with on a package boiler is essentially the expansion tank. And you've got to have, as I had mentioned earlier, the expansion tank is a key component to allow for the safe expansion of the water. As the water warms up, you have to have a place to go with it. If you don't, then you have to have some sort of a relief or something on there. This boiler also happens to have on this system, you can see the cold water supply. You can see the backflow preventer that we had talked about earlier. That's like a check valve. It only lets the water flow one way, and it prevents the fluid within the boiler system to go back into your water that you would be drinking. A pressure reducing valve, we had said typically reduces it from the city water or the well water down to a usable boiler pressure, a boiler minimum pressure. And we happen to have, in this case, we're showing a circulating pump, and we're showing, in this case, 3 zone valves. And again, those are, you can either zone them with pumps, like the previous boiler system, or you can look at it where you use zone valves. Just depends on who piped it and what the specs on the job would have been. So that's kind of one. This one's also showing another interesting little function on here. And this one's showing me a water level control. Now, a level control or a water level control might likely be a device or some sort of a component that would prevent that boiler from operating in the event that you are low on water flow. So if it picks up air or it doesn't have water in the boiler, it'll stop the boiler from firing. That would be kind of a typical way that might be done, but very significant that's needed on those types of applications. So, all right. So another part of a boiler system that we'll do is we can also have the boiler system actually create or make hot water for us. So for people to shower with and use for your washing dishes or clothes or anything like that. So we have 2 choices. One of them is we can either go with what they call a tankless water heater, and that tankless water heater could be inserted. Usually you'd see something like this where it would be inserted into a cast iron section of a boiler system. Those I would say are a little bit more rare. You don't typically see a lot of that. We would be more likely to see what I would consider as an indirect hot water heater. And in an indirect hot water heater, typically what we would do is we would have a heat exchanger that's built into this tank, and that keeps the boiler water completely separate from the water or the potable water that would be going out to the building, that customer, for showering. And so the very different systems is what they would end up having, but that's typically what would happen. It's a very efficient way to operate for your domestic water, let's call it, or domestic hot water. And it uses the boiler all year round. The beauty of them is just the longevity. They last so long, you typically don't have a problem with those tanks. All right, so let's take a look at some of the primary boiler components in this case. So when we start looking at a package boiler, a lot of times what happens is we'll ship that boiler with a lot of the essential and the main components that would be needed to install that system. So that would certainly include all the burners, all the controls, or many of the controls. It usually would include an Aquastat, which is a water thermostat. Usually would have a temperature pressure gauge, and in many of them they would include a pump. A lot of our old cast iron sectional boilers that were put residentially, when you bought them as a package, and they included that. When you start getting more commercial, it's less likely you're going to see the circulating pump be included in that because that's so special to each job. The Aquastat that would typically be used on your boiler system can either be electronic or it could be something that is like a well type system that would be inserted into a cast iron boiler. So there's multiple ways that those would be seen or used on an application on there. But the Aquastat is essentially the water thermostat. So it's designed to control the water temperature either to a maximum in the boiler or a minimum and maximum in the boiler. There's different ways that they'll do it, but typically we would normally see the Aquastat being used to control the maximum water temperature that would be seen in that boiler for that. All right, here's an example or two pictures of a standard Aquastat. Now the one on this side, on item A, this one is nothing more than a water T-stat, a water thermostat. So all it does is you set that temperature in that boiler system, and it's going to either enable it or disable it based on the differential. The one on the right has a little bit more involved in it. And on this particular one, we're incorporating an electronic thermostat, Aquastat, for water. And we also have another feature on it that allows us to use it as a low water cutoff. Now, there are systems out there that will have this. It's not super common, but there's a lot of the higher end boilers that will build these types of things into their boilers because of the critical nature of the fact that you can't run those systems without that. Surface mounted Aquastats. These are not something that I would necessarily want to use as my primary boiler limiting safety device, but it can be used that way in some cases. So sometimes what we'll do is we might have a surface mounted Aquastat on a job. Maybe it's going to say, hey, when this water temperature is up to a certain point, after the pump starts, we'll let the boiler start. We might use it in conjunction with other types of controls, or we might use it in a fan coil that would maybe limit the amount of, maybe they use it to turn the fan on. So on a fan coil unit, they may say, okay, if the water is up to 130 degrees at the unit or 120 at the unit, we'll let the fan turn on. So there's other ways that they can do it, but they do make such a thing as a surface mounted Aquastat. Same thing is apply. You got a temperature setting, you can adjust it, and so on and so forth. But but I don't particularly care for that as a main boiler Aquastat generally. I've seen them used on jobs, and I don't think they generally work very well for controlling and limiting the boiler. I think most boiler systems, you definitely want to have something that's really directly embedded into the boiler to safely control that boiler temperature. So let's take a look at the next one here. I have an electronic low water cutoff. Now, on this particular boiler, usually what will happen is we will have a safe minimum level of the water in that boiler as identified here. There's a minimum safe water level. And if that water level ever gets below that level, this little device here, what it will do is it will actually send an electrical signal that the water will actually act as a path to the ground to prove that yes, we do indeed have water in that boiler. So this tapping right there would be threaded into the boiler, and then the path for those little electrons, they will actually work their way right back into this device and either prove or disprove that you have water. So low water cutoffs are generally required on most of your commercial jobs and some of your residential jobs, depending on the municipality or where you're located. But that would be the idea of a low water cutoff. You don't want to run a boiler without water in them. It's kind of funny because you have a boiler system they call it a boiler, but it really doesn't boil the water. Now, if it were a steam system, that's a different story. But in water systems, they don't generally do that. All right, so combination temperature pressure gauge. A lot of our boiler systems will have a gauge that actually does both of them. It measures both the water temperature of the boiler water, and it also measures the pressure of the water. Now, a lot of these systems, they may vary in pressure. I mean, they may go from 0 to 100 psi. They may go 0 to 50 psi. There's a lot of different applications on there, and it's usually a fairly good indication on there. The one thing I'd be real careful with on these types of systems is if you're relying on this as a very accurate way to measure the boiler pressure, be careful on that. A lot of these pressure temperature gauges, after a certain amount of time, the pressure gauge doesn't work very well, or the pressure setting becomes very inaccurate. So that's the one thing I would be careful on, that if you're relying on that as your sole. Most service technicians will have to have some sort of another pressure gauge to use to verify the boiler pressure. Circulating pumps. What's the job of the pump? Very simply, the pump's job is to take water and circulate it by creating a difference in pressure. So generally the lowest pressure we want in our systems is usually at the inlet side of the circulator, and that should be very, very stable. And the higher pressure, the highest pressure in the system should be at the discharge of the outlet side of the pump. In this picture, I want to point this out. There's an easy way to kind of tell the inlet to a pump. So on this picture here, the inlet to the pump is this bottom little flange, and the water has to flow into the inlet volute and go directly into here, where then the water will get spun and it'll fling it on out into the discharge. And so when I am looking at a circulating pump, I'm actually feeling or looking for this little device there, or that little part of the system, and that tells me follow that backwards and you'll see that, oh yeah, the water flows in this way, and that's usually how you want to do that. So very simple. So let's talk a little bit about the circulator and some of what we have to kind of deal with. So they make, by the way, this pump here, we consider this as kind of a cartridge circulator or a cartridge pump. Most of these little circulators are what we consider as a wet rotor pump, where what they're doing is they're actually using the water or the fluid in the system to act as a lubricant for the pump. A lot of these will have a ceramic bearing that relies on the water in the system or the fluid in the system to actually be the lubricant. Running them dry does not do it very well at all. So that's kind of one thing to remember. So there are some other things to deal with. In circulating pumps, we have pumps that have low head, we have pumps that have high head, we have high flow pumps, low flow pumps. We have pumps that can move a lot of GPM, which we consider as a high flow pump. So there's so many variations. Hydronics is such, I would say, a very much of an engineered type of a job, depending on the application that you're dealing with. So what I wanted to show you in this one is more of a commercial pump curve. And on your residential pumps, you can have something called cavitation. On the commercial pumps, you can run into cavitation. And where that would become an issue is if your inlet pressure going into the inlet of the pump falls below a certain point. Now, there is a pressure, a minimum pressure that you have to kind of stay under. And I'm gonna get my highlighter out here and just switch this over here. And this little line that's right here, they call it the net positive suction head required line. So depending on the flow rate, in this example it's a very high flow pump, they are running, for example, I'll use point A. At point A, the amount of head pressure that would be needed for net positive suction head, if we went straight across to the right, that will identify specifically what the head pressure is needed in there. So in this case, at about 400 gallons a minute of water flow, that pump would probably need about 6 feet of head as a minimum inlet pressure to avoid cavitation. If you have a higher amount of pressure, and this would be related to the static fill pressure, if the pressure would be a little bit higher at the inlet side of the pump, you can avoid that cavitation. So that's something else that is they talk about a little bit more in your book, and specifically what we're worried about is when pumps cavitate, what happens is the fluid that's going into the inlet of the pump actually kind of vaporizes, and usually this happens at the inlet side of a pump. It can happen in if you have valves that throttle flow. There's a number of things that can do that. You have to be really careful with that. So that's kind of one of those that I would identify or point out. So you have to be a little bit careful. So there's a couple other things that we'll also deal with. So in this application, I want to point out a few more things on this one here. So I'll go back to my pen. All of these little 9.5, 9, 8.5, those deal with diameters of impellers. So the little circulator pump, that actually has an impeller. And I'm going to go back a slide. So this right here is the impeller. Now, what they're saying here is the diameter, that would be the diameter of the impeller, is variable between 8, 8.5, 9, 9.5. Now, it doesn't mean that you're changing the impeller diameter with the same impeller. What it means is you have to select the size of impeller needed to give you certain either head or GPM depending on what you're wanting to do or what you're needing to do. So in this example here, if I were to look at a system where you're running, I'm going to draw a line up to here, and you are operating, or they want to operate at this point at 400 gallons a minute of water flow and a feet of head of roughly about 58. Now, this feet of head, we talked about it in the first lecture series. The feet of head was referring to the resistance of the water flow. That's what the pump has to overcome. So due to the viscous friction in the water of the system. So this is what you need to overcome, the resistances of your valves and your piping and heat emitters and things like that. So that has to be figured out. In a system where I want to move 400 gallons a minute and 58 feet ahead, you can tell that there is no way that I could use anything less than an 8-inch type of a pump impeller diameter. So 8-inch wouldn't give us any wiggle room at all. It might be better in this case to have a little bit more capacity on the pump and maybe put an 8.5-inch impeller for that system. But that's, again, the engineers generally have to make those selections. I also want to hit up on an application on these applications where we're starting to look at, we're going to look at these numbers here. So on your pump, we're showing 50, 60, 65, 70, all the way up to a maximum of 83.5%. What that represents is the efficiency of the pump in transferring that mechanical energy to the water, is where that is. So it's a function of the efficiency of the pump. We obviously would want a pump that has the highest efficiency that is possible. And that's challenging in some cases. So if we're in that middle third range of a pump, we usually can get the highest efficiencies. Anything that if we run closer to this side or even further out here, as you can tell, the efficiencies are going to be decreased a little bit. So pump efficiency is important because it affects our energy consumption on the pumps. Also on this curve, you're going to notice that they give you some horsepower requirements. If you're going to select a pump on a commercial job, the engineer has to select a pump. Well, he's got to know what size motor is going to be needed for that application. So if I were to run a system, and let's say I open up a bunch of water valves, and all of a sudden, before you know it, if I were running at this point right here, and all of a sudden I open up some water valves, I could very well run on that 8-inch curve, this 8-inch diameter curve, I could very well be overloading a motor. So I'd have to be a little bit careful of some of that goes on there. So that's a little bit on that. So be sure to read through that section in your book on the pump curves and being able to kind of read it. So all this, the essential parts of a pump curve is identifying our capacity in GPM. It identifies the amount of head that the pump creates as far as pressure, and that's what's going to be used to overcome those resistances. So in a circulating pump, those are the two most important parts of that circulating rating system that allows us to determine our flow in a system. So, all right. Well, even more advanced circulators, nowadays they make ECM circulating pumps. And what we're doing is we're taking advantage of a motor that is extremely efficient and allows us to enhance or take a motor that might have been, previously like a PSC motor might have only been in the, 50-60% efficiency range. And we can now utilize a pump that might be more closer to 75-80% efficient. Just like we've done in furnaces where we've taken a blower with an ECM motor on it. So this is a kind of a current technology that is out there that does a really nice job. But ECM pumps, they do a great job, and they also give you the ability, the manufacturers can program certain parameters in there where you can say, I want it to maintain constant speed, or I want to maintain a constant pressure, or I want to do the best that they can to try to maintain flow. So it gives you a lot of variability. They're really awesome. In this application, we're going to look at an ECM circulator that we're going to be looking at. What this one is called is a variable speed delta T pump. And this is an ECM pump that they're showing. And we're going to look at the temperature on the return side and the temperature on the supply side. And when you have, let's say, only one zone calling, you don't need as much water flow. So what will happen is the pump will tend to kind of throttle back a little bit. It'll slow down, and of course the boiler will recognize that, and it won't create quite as much heat. So depending on the system you have and the complexity of the boiler system, you may have a system where you could have a variable pump and you could have a modulating boiler or a multi-stage boiler that could very efficiently control the system to give you the proper amount of water flow. They're really outstanding. They do just a fantastic job. I've seen some of these applications where they're running both. You can maintain constant pressure for a zone system. That would be the best scenario. Or you can look at it from a standpoint of variable speed. There's a number of different ways to do it. So, but it's the current technology that they have right now. All right, so looking at air and water controls. So one of them is, obviously we have to look at how are we going to get this, how are we going to control water, how are we going to control air, things like that. These are a number of these that we typically have. So let's take a look at it. So the first one that we're going to deal with is the standard expansion tank. And one of the reasons in more of a conventional expansion tank system, What we're going to typically have is when we're operating and normally running, we typically want to have roughly anywhere from about what I would say is about 35. There we go. I want to have somewhere between 35% to 50% is what I want to have as water in this tank. Now, when you're up and operating, the rest of the room has to be for air. I need this to be air, just as it says right there. And that's really simply allowing us to have the safe expansion of fluid in that system, so that we don't burst our boiler or any types of piping that would be in there. Typically on a lot of the older systems, this also was our air separator. So a lot of these older systems, we would have expected a lot of those little bubbles to kind of make their way up into the boiler system, and they would have kind of, that would have acted as an air separator. There's a downside of this. Problem you have with these old tanks, so these old expansion tanks, is over the time when you're not running them, a lot of the air in the tank tended to want to kind of migrate and be absorbed into the water that would be in here. So all of a sudden, as you took some of the air out of the tank and you put it into the water, that a lot of times what would happen is then the pressure in the system goes down, and the fill valve will make up that water pressure and it'll build it back up. So eventually, the problem you run into is a lot of these tend to get, let's call it waterlogged, is what they end up having. The diaphragm type tank is an advancement that had been, we've been using these for the last 30 years, and the diaphragm type tank really, we would pre-pressurize the expansion tank and set it up. Usually most of the jobs we would set it up as a 12 psi pre-charge, but this really has to be set it up. You want to set this up to whatever that expected pressure would be in your system. So wherever you locate this tank right here, that's where you would want to have, wherever you locate that tapping, you want to set that up to that pressure. So most residential jobs, you're going to be somewhere in that 12 to 15 psi range is very typical of what you would see. Now, also, this tank should also be located, if this is my circulating pump, you generally want to see this tap and connected somewhere at the inlet side of your circulator, right in that area, in that general vicinity. Now, as the fluid in the system gets warmer, then the water kind of expands. It pushes that diaphragm over this way, and it expands it, and it compresses that air in that system. And so that's typically what ends up happening in most of these. So the beauty of this, there's generally less water logging where we don't typically lose that air, but it does happen. Other air control devices. So we have devices in the system that are, let's say, more active, and there's some that will do some to do a better job than others on trying to get rid of the air. So for example, in this system, this is an inline air separator. We would have water flowing into this particular system, and hopefully it's the warmest water, and then we would expect the air bubbles to kind of make its way out of there, and you would probably have some sort of an air vent, an air separator, or a little air bleeder, auto air vent that might be located on top of there. That's one way. There are some of them that are a little less common nowadays, which are called air troll boiler fittings. This actually contains a dip tube that would have gone inside of a boiler system. You don't typically see a lot of those on a lot of the systems anymore, primarily because of the advancement in our systems. This one here, the Spirevent one that's shown here, this one's actually a vertical air separator, and where the water kind of flows into this thing and makes its way back out. And we're expecting those little air bubbles, those little micro bubbles, to kind of make its way out. And there would be an air vent off the top of this one. So again, a few different types of systems out there. Some do a better job than others. Pressure reducing valve. Typically, they come factory set at 12 normally, depending on the model that you choose. For most residential and light commercial jobs, they make them in larger systems, but this same one that you see here is also the same one that we use in many of our commercial jobs. And its intended job is to maintain a minimum inlet pressure to the boiler, and that is the extent of it. It is not intended to act as a relief valve or anything like that. It's really intended to reduce the pressure of the incoming water down to a workable level. The pressure relief valve, it's got a job, and its job is really intended as that boiler warms up and that water expands. If there's any situation where the pressure in the system or the boiler system exceeds the pressure in any closed system of its pressure rating, this valve needs to be able to relieve it and allow that water to kind of push that little diaphragm out, let's say, and then essentially expel that water and relieve that boiler of its pressure. This could be, or maybe you had an expansion tank that became waterlogged. It could be something, again, you have to be very careful of that, that make sure that those are functional and working on a system. So that's most of the time, I would say the most common pressure that those relieve at is typically about 30 psi of pressure. Makeup water and corrosion. So earlier on in the first lecture, I had talked about how the makeup water system, as you bring in enough water, it has a lot of dissolved oxygen in the water, and that's a challenge because we have to be able to get rid of that. On a system where you've got ferrous metals, one of your concerns is that the oxygen or the air in that water will create problems for you, or it'll rust out, or it'll corrode some of your heat exchangers and things like that. So you have to be a little bit careful on that. On a system where you're running all non-ferrous metal components, it's, I would say, less of a concern or less of a deal, but it certainly is a concern with any component. So for example, even if you have all non-ferrous components, if you happen to have a boiler system or a circulating pump in the system that's cast iron, you now have ferrous metal components. So that will tend to create a problem for you. The whole goal of this is in any closed hot water system, we want as little makeup water as possible is what we want to do. We want to try to minimize that. So that's really the goal of that. All right, so let's take a look at zone valves. So this is showing me one style of zone valves, and one of the things with zone valves is we don't want them to slam open or slam shut. When we open up a system, we typically want them to kind of drive at a certain amount of time. And that could be, 15 seconds, it could be 30 seconds in some situations where they would open and they would close at those kind of time periods. It's primarily to prevent a lot of water hammering effect on those. So that's really kind of one of the reasons for that. This one here happens to be, that's made by Takeo, is a type of a ball valve type of a zone valve. And it's got a little actuator. This one here has a little push button device that gives you an indication of the position of the valve, and you can usually manually open those. The other thing that I like about this zone valve is that I have two removable electrical terminals that I can pull off, and I can put my wiring on, or if I have to change a power head, I don't have any wire nuts to deal with at all. It's really nice on those. They're very removable, very easy to work with, so they are, it's a nice little system on there. So the other advantage that I like on some of these is they have a very high CV. So for example, on a lot of my systems, if I want a high CV, if it's a two-position system, I can control my water flow very effectively. All right, so earlier on we had talked about these backflow preventers and what their job is. Now this one that's shown here is very much a commercial backflow preventer that has multiple test ports in there. The whole goal of this is really just as it's described, just as it is described here. The whole goal of this is we want to prevent any type of water that would be in the boiler system from going into the domestic water supply and contaminate that. This is especially important when you have glycol in a system. You have to be very, very careful on that. So a commercial one like this, they require them to be maintained and certified on an annual basis. They're residential, we don't typically see stuff like this. It's where you don't have to recertify them. Typically is what would happen. Now there are a couple little things in here that I want to point out. On all backflow preventers, there needs to be some sort of a vent port, and that's what you're showing there. And that vent port will discharge into some sort of a line, what we're calling is a relief line. That is not relieving due to high pressure generally. What it's doing here is it's going to discharge in the event of a failure where it will allow the discharge of the fluid in the system to vent and go directly into this device. Now this one's also showing me, and it's also showing an air gap. Now that's usually a requirement for most systems. Now the air gap in a lot of your commercial jobs are going to be put up high. On a lot of your residential jobs, the air gap will be placed at the bottom of where that tube goes, and that's typically very essential to have shutoff valves. And it's really helpful to have shutoff valves before and after those backflows. But residential, you typically only see a shutoff going into the backflow and a shutoff after the pressure reducing valve that would be in there. So that's typically what happens. One way, it's all they let you do. It's basically a check valve. All right, so in the, we're going to look at some check valves here next. So the first one I want to deal with is a way to prevent, let's call it flow when we don't want flow to be moving through there. And this type of a check valve, what we're going to call is like a ball type or a swing check valve. One of the differences that you notice usually on some of these types of things is they only allow water flow in one direction. And these generally have very low resistance. So when the circulating pump kicks in, it takes that little disc and it swings it. It moves it up and allows the water to continue. On this one here, we have water flows into here. It has to push that ball out of the way and then make its way through there. It's just a different design. They're doing the same type of a thing on there. The idea is to prevent any type of reverse flow that would be needed on there. Most of the time you'll see a spring, some sort of a spring that would be into here that would prevent that ball from moving, or I've seen swing check valves where they have a disc. So a lot of different ways on there. All right, so let's take a look at some of the valves. So we got a few different types of valves. The first one I want to hit up on here is a gate valve. Now a gate valve should never be used for modulating flow. The only purpose and the only real use of a gate valve would be that for just purely shutting on and off or turning on and off water flow. I need it for isolation, and that's the only use for that. They have a disc that's shown right here that would be driven down by a threaded piece, and that little disc will slam down and it creates a very tight seal on there, and that's kind of one design in there. The downside of these gate valves is that there's really no good way for you to notice whether the valve is open or closed. So that would be maybe a downside of that valve. Another valve that's used that's a little more common for isolation nowadays and also for flow would be ball valves. Now, you know, for many years they would say don't ever use a ball valve for controlling flow, but they actually do work, and they've designed a lot of the valves to allow you to control water flow for that. But it's a great isolation. The beauty of that is that you have a handle and you can physically see the position of the valve. So in this picture here, we're showing a valve which is allowing water to flow through there. If I were to turn this handle and move it at a 90-degree angle, by turning that one at a 90, that would take the water that's flowing through this ball valve and it would stop it. It would prevent it from moving. So if, again, it's just a 100% rotation. So 90 degrees at a time. A globe valve is probably our best valve when it comes to adjusting and maybe moving, allowing water to, we want to adjust the water flow rates. Ball valves are used in some situations, but the globe valve is really one of the better ways to do that. It's a great way to adjust the flow. It's a throttling valve. You can use it for isolation, but most people aren't going to do that. They would use a gate valve in that case, or a ball valve. So this valve is set up almost like a Z arrangement where the flow moves into here, has to make a connection, go back up, and then essentially make its way out. So this little disc that we're showing you here has to move up out of the way to allow the water, either more or less water, to flow into that system. So very nice little setup on those. An angle valve is really almost, it's very much like a globe valve. It's just at an angle, you have your threaded connections 90 degrees from one another. So very, very much the same types of things. 2- and 3-way valves. So the only difference between a 2-way valve and a 3-way valve are the number of ports. So we have, you can have a 2-way valve where you could be modulating, where it could give you anywhere from 0 to 100% of the water flow, and we're talking about this valve up here, that's a 2-way valve. It could be 2-position, where it's either open or closed, or it could be anywhere in between. That's a very common way for systems to control the water flow nowadays, especially with the new technology that's out here with variable flow controls. On your commercial jobs, you could either have it could be a 3-way mixing valve, or it could be a diverting valve. And the difference is essentially the number of inlets. So on a mixing application, we would have it where there would be 2 inlets that would mix and give you 1 outlet, or such as you have some hot water and some colder water, and you'll come up with a mixing outlet. Or in this example, what they're showing in this picture is they are showing this valve used as a diverting valve. And what they're doing is they have 1 inlet and they have 2 outlets in this case here. So it just depends on the piping layout of that valve. So you generally want to look at the manufacturer's recommendation on piping those to know specifically the type of valve that you're dealing with on here. So very, very good. They can be, you can either use them either or in those cases. So just watch that. All right, so a little review. Gravity hot water heating system would typically have, I would say most likely, no circulating pump. So a low temp, low pressure water boiler would be typically limited to, limited to 10 psi max, I would say not. Used only in gravity systems? No. Found in homes and apartments? Maybe. Limited to a 200 psi maximum? No. I would say typically found in homes and apartments. During cavitation. Cavitation is when we vaporize the water. So let's see what this one gives us. Discharge pressure increases? No. Pump becomes quiet? No. The pumps are loud when you have cavitation. Some water vaporized at the inlet point, or the volume of water flow increases. Definitely vaporized at the point of inlet. Which type of valve, or what type of valve is the best for throttling flow in a hydronic system? So I would say we can get rid of check valve. It's a globe valve. You could get rid of gate valve, and obviously zone valve would be iffy on that. So the globe valve is the best valve. So that was the extent of section 2 on there. When you're done with this one and reviewing that section in your textbook, you may proceed to section 3.